Welcome everybody to tonight's talk. Today we have Mayank, who will talk about neurosymbolic approaches for robust domain-specific semantic search, specifically about current progress and future opportunities. Before we go into the talk, let's say a few words about what this party is. So this is part of our talk series on knowledge graph research. Today we have Mayank Kejriwal, who won the Swissa Distinguished Dissertation Award in 2017. We have a few past talks that you can find on our website, and also we have a few more upcoming, which we will schedule on top of those we already have. So we have Mark Mewson coming up and Peter Patel-Schneider. This talk series is organized by a Cost Action, which is a European research network where over 30 countries are represented. It will run until September this year. It's led by myself, Axel Polleres, Michel Demontier, Remzi Chelebi, Andreas Hart, Antoine Zimmermann, Olaf Hartig, John McCrae, Anastasia Dimou, and Stefan Gostojic. Tonight, we have Mayank, and I would like to hand over the word to Olaf, who will introduce Mayank. And I want to say have fun with the talk, because that will be a seamless transition then. So, Olaf, over to you.
So thanks, Tobias. Welcome from my side to you all. Thanks, Mayank, for being here. So Mayank is a research assistant professor at the University of Southern California. And additionally, he is also principal scientist at the Information Sciences Institute at the same university. He received his PhD in computer science from the University of Texas in Austin. And as Tobias already mentioned, for his PhD, he was awarded with this Distinguished Dissertation Award of the Semantic Web Science Association in 2017. Nowadays, his research is related to applying neurosymbolic AI to real-world complex problems. Especially the interest here is in combining the benefits of knowledge graphs and generative AI models. And I think this is also what the talk will be about, including reflection on the dissertation. So I'm really looking forward to seeing the talk and hearing what Mayank, what you have to present to us. The floor is yours.
All right, thank you very much. So I will start sharing my screen. Is everything visible and
Perfect.
Yep.
Good to go? All right, great. Yeah, so thank you for inviting me. I am very excited to be here. And the talk is titled Neurosymbolic Approaches for Robust Domain-Specific Semantic Search, Current Progress and Future Opportunities. And I'll begin very briefly, just to say a little bit about my project. So, you've already heard the introduction. And so there are two kinds of projects that we are very interested in both my current research, but also my recent research since my PhD. And as you can see here, some of these are applied projects. So they might be commercial, such as e-commerce or healthcare, which we are working on right now. But they could also be applications to social good problems like fighting human trafficking, on which we have presented at ISWC, and developing systems for effective crisis response. And both of these I will say a little bit about in today's talk as well. Now, on the other side, we also have some more what we call fundamental AI projects. So these are projects where we are trying to, they tend to be more application agnostic. We are trying to develop approaches, methodologies, evaluations for general problems such as common sense and dealing with novelty. So can we build AI that can react to unexpected events? So that's this project. So I won't say too much about these projects today. So I do want to acknowledge everyone who's worked with us on these projects, it does take a village, which also makes it a lot of fun. And so first, a lot of our projects are funded by DARPA and some by IARPA, but we also have funding and support from companies such as Kaiser Permanente and Yahoo when it was owned by Verizon. Media, now it's independent. And we have a number of collaborators from industry and academia alike. So we're very grateful to all of them for working with us on these problems. So what are my goals for this talk? So the title was a little bit longer, and so I want to break down the title in some sense into some specific goals that I have in mind for today. And the first goal is to introduce domain-specific search. So this is kind of this was the sort of problem that we are looking at in many of our applications. So I do want to tell you a little bit about what this is, because it's very difficult to find definitions of this problem. It seems self-apparent when you hear the term domain-specific search, but I do want to say a little bit about this and show you some applications, some of which might be unexpected. And then we will go into two specific DSS systems that we built in our group over the years that we have presented in several conferences over the years. And we never called these systems neurosymbolic systems, but when we look back, we see the neurosymbolic philosophy in these systems very clearly. And so for that reason, I do want to look back at some of these systems, which are still very recent, and frame them as neurosymbolic. And then based on that, I will conclude by coming to this topic of large language models, or LLMs, and knowledge graphs. And the third part of this talk is really more perhaps opinion-based, if you will, more sort of my views, lessons that we've learned. We'll try to distill those. So you may or may not agree with everything in part 3, but hopefully it will provoke, some thoughts as you hear those. So let me jump right into the first one, which is introduce domain-specific search. So what is domain-specific search? Well, I like to use quotes from previous papers that have used this term. So one of the earliest sort of meaningful quotes that I found from Andrew McCallum's paper in HCI in 1999. So this, of course, if you look at the timeline, 1999 is kind of when the web had really taken off, right? There was no doubt that that it was this huge thing. It's changed the world. It was very clear by then. It had grown exponentially. As we know now, right? Just 2-3 years later, Tim Berners-Lee would also write his Semantic Web article in Scientific American. So we were thinking ahead by this time in some sense. And so what Andrew McCallum said was that domain-specific search engines are becoming increasingly popular because they offer increased accuracy and extra features not possible with general web-wide search engine. It was kind of pre-Google. I think Google had been formed by then, but it wasn't a big company. It was still a startup. He doesn't define domain-specific search, though. This is the closest I've been able to find in the paper on what he really means by domain-specific search. When we know that we want information of a certain type or on a certain topic, a domain-specific search engine can be a powerful tool. So from these, we can distill that, look, it's domain-specific because we might want information of a certain type or a topic. That much seems clear. But also the reason why we want these over a generic search engine is that they may have more benefits. There could be increased accuracy and more features. So I want to keep that in mind as we go into the actual two systems that I will show you. And then much more recently in a journal article, Schmidt says that common domains are products, restaurant, hotels, scientific publications. However, they don't mention social good applications, and so that's why I want to focus on social good applications today. But these are all good commercial applications. And they bear advantages by exploiting knowledge of their domains in order to improve the search experience for the user. So it's compatible with what McCallum said, 17 years ago before this 2016 article. So hopefully this gives you a sense, which aligns with intuition as well, for what domain-specific search actually means. And as Schmidt pointed out, domain-specific search has many application areas and challenges. So here what you see is that even in industry surveys, and this might again comport with your own experience, that when you're looking for a product, you are more likely to go to the e-commerce retailer directly, whether it's Amazon or it's some other retailer or aggregator of products. If you're looking for videos, you are more likely to go to YouTube. If you're looking for restaurant reviews, you are more likely to go to Yelp, and so on. And all of these are implementing domain-specific search engines. They are not using ordinary Google search. So Yelp knows that you're looking for restaurants, you're looking for certain kinds of entities, and you have a certain intent in mind. I mean, you're not going to go to Yelp to learn more about a politician or a scientific topic, right? You're going to learn to, you're going there because perhaps you want to make a decision on a restaurant, or you're trying to choose between restaurants. So there's a different intent, and that can be exploited when you're building a domain-specific search engine. Another interesting problem, and we have briefly looked at this in our own group, but I want to give you a couple of interesting applications, something you might not expect, kind of to expand the horizon for domain-specific search. One of the very interesting problems is building situational awareness for assessing cyber attack vulnerability. So this is a very ambitious problem that is still very interesting, which is, that can we use things like exploits, software exploits that have been released, social media, news articles, etc., and also previous cyber attacks to answer questions like which companies are vulnerable, or can we build a profile of a specific attack? Who was attacked? What was the ransom? What are some patterns? And and so on, right? So it's a very challenging problem because the data is hard to get, hard to combine, and so on. But this would be an example of DSS, whether we do it right or not. But it's not. You can't enter these questions into Google and get very good answers. So you do need a domain-specific platform that is focused on cyber attacks, for example. Another application is building human-machine super forecasting teams. So this term super forecasting was proposed by Phil Tetlock, who is very well known in psychology and social sciences. And forecasting is different from prediction. So forecasting is you're trying to predict the future outcomes. And usually, unlike prediction, even humans are not always good at this. So you can't get labels from humans. So for example, if I ask you what's going to be the price of crude oil next month, right? I mean, you probably get a wide range of answers. And so who's correct, right? I mean, it's not random on the one hand. On the other hand, there is a wide interval. Now, it turns out that interestingly enough, there's a small group of people who are very good at making forecasts, and they have been studied in the social sciences that how do they do that? And it turns out that they are really very good with information. They know what information to get, how to process it, how to frame it, how to do it. And so one of the questions here is, can we build domain-specific search engines to make ordinary humans into super forecasters? This is also a very interesting problem that we looked at and others looked at as well. So those are just some interesting examples, hopefully, just to kind of with the goal of convincing you perhaps that it's not just restaurants and products and so on. There are interesting applications of domain-specific search. So now let me jump into two specific systems that we have built in our group and that we now see as neurosymbolic instances. And obviously, before I go into the system, I do want to say a little bit about what we mean by neurosymbolic reasoning. Again, it's one of those terms where it's easy to look at the term and assign a certain meaning, but it's also good to look at what the literature is saying and why we should use neurosymbolic reasoning. So we always like to use this example from common sense reasoning, right? So this is an application agnostic. So let's say I asked a question like, this is a common sense question, that on stage, a woman takes a seat at the piano. What does she do next? Now, there's no logical, kind of next step to this. I mean, she could do any number of things, logically, right? I mean, one answer is she sits on a bench as the sister plays with a doll. this is not impossible, right? She might do this. You can't prove that this is not true. And answer 2 is she nervously sets her fingers on the key. Now, this is much more likely. The answer 2 is much more likely. It's a common sense answer. This hopefully shows you, interesting things about common sense reasoning as a problem in AI. And one way to do this is perhaps we send this into some language model or even large language model, and it would give hopefully answer 2. And so we might argue, well, the answer seems obvious, and yes, if you send it into a deep learning, you will get answer 2. In fact, it turns out that it's not. There are many questions like this that we would find obvious, but the machine does not find obvious. Even very deep learning systems can make a lot of mistakes on questions like this. There's a huge body of work on that by now. So it's not. It still seems like even if you train it, there's something can go wrong with this deep learning model, this black box model. And you can't always. There's always a question mark. Will it give the obvious answer? So one of the goals of neurosymbolic reasoning is that not only do we want the answer, but hopefully we can get more out of the overall system. So through some kind of symbolic reasoning, whether it looks like this, where instead of just saying, oh, the answer is answer 2, a way to think about this is, well, why, right? Why answer 2? And there's a connection to XAI, but it's not exactly explainable AI. Instead, we might say, well, maybe it's good to break up this question into a semantic frame, right? Whether that's a knowledge graph or just a normal graph, some kind of other graph. But I would call this a semantic frame. So there's a semantic frame, and the semantic frame gives you the semantics of the question and the answers. And then through the semantics, we might be able to figure out that the answer 2 is the right answer because she's about to give a performance, and performances usually implicate nervousness for most people. So she's nervous, and this is kind of the guiding word. You can see the context is nervous. Whereas for the first answer, we're not really seeing a strong context that can come in. So we need to do all of this automatically. This was the goal of the machine common sense program, where we did propose a neurosymbolic approach. But this kind of shows you, why this kind of approach is useful. And you don't just want the deep learning to give you the answer to. You want something more like this, where there's more semantics in the answer. There's more semantics in why we pick answer 2. What's the triggering word or words? What's the context? What's the frame, right, in which answer 2 makes sense? So some definitions and perspectives. This is a bit of a dense slide, but it's useful. And I like to go through the literature a little bit on these things. So the core intuition, of course, is that instead of thinking about neural and symbolic reasoning as rivals, why not aim to combine the best of both? Some think that the probabilistic reasoning should also factor into this. Other definitions which are more grounded in psychology see that it's a robust enough connectionist methods, which include neural networks, but is not always limited to neural networks, and the soundness of symbolic reasoning to effectively integrate learning and reasoning. And then perhaps a very simple definition is it's a combination of deep learning and symbolic reasoning. And the real goal behind doing neurosymbolic reasoning is that because you're invoking the symbolic principles for reasoning, there's a lot you can get out of it that a black box is not going to give you. So there could be more domain transfer. You would be able to deal with out of distribution inputs, hopefully more flexibly. There would be more interpretability. We could deal with reduced data by relying on fundamental reasoning principles. And of course, high level reasoning, which is still very suspect in even large language models. So neurosymbolic reasoning usually depends upon a robust symbolic representation. This is from Bader and Hitzler, this frame, right? And, I would argue that by robust symbolic representation, it must be amenable to construction from raw data. So a lot of the data in real domains comes from these raw data, right? Like text and images. It doesn't come to us as well-defined triples in a lot of cases. So we do need to extract things from it. So we should be able to construct the symbolic system from raw data. We want the symbolic system to be accessible using the connectionist system, right? So is there some way in which the large language model or some other system can interact with the symbolic system? whether it's graph convolutions or embeddings, etc. But we also want it to be accessible using querying. So we don't just want the symbolic system to be absorbed into the neural network, because then we lose the benefit of the symbolic system, right? So we do want access through querying as well. And we want a wide range of semantics to be supported. So on the one hand, to support expert knowledge and reasoning, you do want ontological semantics. But on the other hand, you also want distributional semantics, especially if you want to access the system using neural methods. So this is sort of a technical view into neurosymbolic reasoning. But there are, of course, many features and benefits. And, there are, again, some quotes here, but I'll just say that one reason why it's so important is that even now, even with all these huge models with billions and billions of parameters, symbolic and abstract reasoning is difficult to achieve with purely neural representation. So at least a partial symbolic representation is needed, right? And this is kind of where the community is doing a lot of research. Multiple communities are doing a lot of research on how exactly to do this. What's a good symbolic representation? What are operations? Do they have to be purely symbolic? Can they be neural or symbolic? How do we reconcile? So these are all very interesting areas of research that are happening. So what are some domain-specific search domains where we have applied these principles? And here are three that I can give. There are others like e-commerce. I will go a little bit into the human trafficking and time permitting into the crisis response a little bit. But I do want to say that addressing these adequately implicates the same goals as those stated for neurosymbolic AI. For human trafficking, for example, we do need things like out-of-domain generalization. We do need to deal with long-tail data. We want interpretability. We don't just trust answers that come from the system. And by we, I really mean the people who are doing the investigation, the non-governmental organizations, investigators, government, etc., who are trying to find human trafficking victims, rehabilitate them, and then fight for justice on their behalf, right? They can't just trust answers given to them by a machine. They need to have some provenance, some kind of reason. So for human trafficking, that's the first system I want to jump into. And the basis for the few slides I'm going to present on this is this article that I published with my colleagues, Pedro Zekeli and Craig Knobloch in IEEE Intelligent Systems. But this is sort of the most accessible version of this work. But a number of pieces of the work, like querying and information extraction and knowledge graph and so on, have been presented in ISWC and in other venues as well. So that lots of papers have been published on this in this domain, but I'm focusing on the overall system in the next few slides. So before going any further, right, I should just point out that human trafficking is the fastest growing business of organized crime. It's a huge problem right now, and it's the third largest criminal enterprise in the world. So this is a really huge problem. It doesn't seem to be getting any better, unfortunately, over the years. And even in all countries, I would argue, this is really a problem, including even in places where there are strict laws, etc. It turns out that it's an age-old problem, unfortunately, and technology has lowered the barrier to entry. So here are just some statistics, but you can sort of see that it's a big problem, even here in the US, in many other countries as well. So it's very sobering. And so the question on the technical side, right, that we asked our entire group over a period of 4 years was how can we make large-scale investigative search easy, useful, and efficient for human trafficking investigators? So this was our guiding question. That how can we, and we didn't focus on solutions. We were really focused on the problem. This was very important. We didn't care what we had to use. If we had to use NLP, if we had to use Semantic Web, if we had to use some other method, we were not thinking about that specifically. We were thinking about, well, this is the problem. How can we best solve it to make a difference? And hopefully the things we know, including Semantic Web, can play a big role in this. So investigative search is, in fact, a domain-specific search problem. And here you can sort of see three kinds of queries that are specifically of interest. One of them is the query that we would generally be interested in, which is called the point fact query, where you just kind of ask locate the entity or the ad with this criteria, right? So very simple. It's a select where query. Then there's the cluster queries where you don't just want one ad, but you want a set of ads or a set of entities that share something in common. So this is more challenging because on the one hand, right, you can interpret this literally and say that, okay, if you share like any one of these things, phone number, email, or street address, and then there's this phone number over here, and then this ethnicity over here, then we should return all of that. But here's the problem, right? So when investigators actually enter a query like this, they are willing to be flexible. So they might say, well, okay, if you don't see this ethnicity inside the ad, but you do see the phone number, then we still want it in the cluster. So you might argue, shouldn't they then make the question much more, much more specific? But if you do that, you lose the investigator. They would be like, well, they don't think logically necessarily, right? They have a different, they have a lot of deep expertise in their domain, but they are not trained to think logically. Most people aren't. They won't be able to give you, they can speak in natural language. They can't speak in logical language. And this is just a reality. And then you have the aggregate queries, which again, you can see sort of the queries, and they are complicated, right? So what's the challenge over here? Well, the investigators will say something like this, right? That is in natural language, and they will not even mean it completely literally. So there's a soft interpretation on the actual query text. Sometimes it will be ambiguous. Some information will not be specified or will not be specified clearly, and the actual queries are quite complicated. Now, we might not think it's complicated if we do this for a living, but most people, even in computer science, who are not exposed to databases, would find this complicated. They would not be able to write this. If they do, most likely there would be an error. Then you would have to correct the query. It's the same problem with programming, right? If you don't know how to program, then it's kind of difficult to convert, something from natural language into a computer program. And so on, right? So, to look at this more conceptually, the investigative information needs can range from properly specified factoid to relatively open-ended exploratory queries. I think that in the querying literature, we still haven't incorporated this kind of design thinking into a lot of our work. We sort of assume that the query will always be well specified, or there exists a proper query for the intent. But what we have learned from conversations with domain experts is that, in fact, many queries can be exploratory. They don't exactly know what they are looking for. So they have some need, and then that this needs to be issued as a query against the database. And then based on the results, they might refine the query, and and so on. And we often do this in Google, etc., right? But with domain-specific search engines, as McCallum pointed out, you can't really answer these kinds of queries, right, using Google, because Google will just give you all the results, first of all, and then a lot of this other information, it will be missing. Google is not extracting this. It's taking a keyword view still. So we need to build a search engine, domain-specific search engine, that will allow us to answer the spectrum of queries, that can facilitate the spectrum of queries. And then that can also do things that the generic search engine can't do, because we can't force anyone to not use these. So if what we are doing is as good as these search engines, Google or Bing using ChatGPT, then no one is going to use our system. So we need to do things that cannot be done by those generic search engine. So why are answering these so challenging in the human trafficking domain? And as many of you probably know, right, one reason is that the information is embedded in millions of web pages. So we need to find these web pages. There needs to be a domain discovery, because we need to find relevant web pages, domain relevant web pages. And then it needs to be read, extracted, and linked into something like a knowledge graph. This is not an easy problem. It becomes even harder when you look at specific domains like this, which have a jargon of their own, and which, they can be complex. The subject matter is tricky. There's not training data available usually. There can be obfuscations, which are what you see over here. They can be ambiguous. So, kind of building information extraction and other methods for this is really hard. So let me jump to our solution. And what we kind of devise for this, and you see a high-level architecture on the right-hand side, is a system called DIG, or Domain-Specific Insight Graphs, which is an end-to-end search engine for assisting investigators in fighting human trafficking. This system was developed, it's been published in multiple places. So here are just three representative publications, but there's one that was also presented in ISWC in 2014, I believe. This is before I was on the project. And that paper that was led by Pedro Zecchelli, I think even won the Best Paper Award. So, this has been worked on for at least 4 years. I'm just showing some of the papers where I contributed. But this is the overall system, and it has been transitioned and evaluated. But as you can see over here, everything begins from the web. But there is a process of domain discovery. There is an ontology development. This is also important. The domain discovery will give you domain-relevant web pages. Then we need to do knowledge graph construction. Now, this is a small box here, but this covers a world of techniques. And I'll come to that right towards the end. But then you get the knowledge graph, and now you can build a search engine. And the hope is that the user enters the questions through some interactive graphical user interface. And then somehow we can convert it to the query. We can access the knowledge graph, and then we can return the results. So there's a lot of challenges in all of these different boxes and arrows. If a more technical view is something like this, where you would need to extract information, right, as I showed earlier, then there would be some semantic modeling. This is reconciling the extracted information to the ontology, doing entity resolution, reconciling duplicates, doing entity linking. To answer cluster queries, we also need to do some clustering beforehand, and then we need to put it inside the database. At the time, we used Elasticsearch. Since then, graph databases like Neo4j and Amazon Neptune have all come a long way, but they were not around at that time, or were not fast enough. And then there's a question on Spring Engine and the GUI. So a lot going on here, a lot of details here. But one of the things that I want to sort of convince you in terms of the neurosymbolic approach is, we have to get away from this notion that there is a one, sort of a mega algorithm that will just solve the problem. So when we analyzed information extraction, for example, right? So most of these come from the glossary is just a dictionary of words, it's keyword-based, regular expressions. These are classic techniques. Conditional random fields and named entity recognition are the more machine learning-centric techniques from the NLP community. NER here we meant this to mean a deep learning system for NER. But when we analyzed this on a scale of 1 to 5, with 5 being very good, we found that they were all over the place. They depended on the entity we were trying to extract. So, for example, glossary is very good for, let's say, locations but not very good for names. Because in the human trafficking domain, right, they use very unusual names. They obfuscate the names. A regular expression can be good for emails, but you have to design them. You have to write a lot of rules to capture some of the patterns. A CRF, NER require a lot of training data. So sometimes it works, but other times, it just doesn't work. Recall can be very low in particular. So how do we deal with this? If we can't have one algorithm for IE, what can we do? And this is where the symbolic representation becomes very important. So we apply the neural methods, we apply the rule-based methods, we get the information, extracted information. But what next needs to happen is that, instead of figuring out what the one right answer is, which is very difficult, if we can even determine it, we instead have this knowledge graph in the system. Now, in most knowledge graphs, you will just see this kind of fact that the event 1, 2, 3 is in location Smitha, but it turns out that what the DIG does is that it is very open to the fact that this fact could be wrong, or at the very least, we may not be confident about it. So we want supporting information. We want provenance. We want confidence. We want to know if there's a qualifier, is there a date, right? So, I mean, we are familiar with this kind of representation, of course, in semantic web. But you know, the key point is that all of this is being extracted automatically and then being put inside the graph database. So this is really important. Why? Because when we query the noisy database, and the database will be noisy. So this is something we learned very early on, that it will never be the case, yeah, even today with the large language models, that you will get a very clean database. So this assumption needs to go away. When you extract from raw data, the data will be extremely noisy, and the noise is not random. I mean, in our case, we believe that even 80% accuracy on some attributes was as best as we could get. On many attributes, we're talking 60% accuracy, and so on. And so it's important to extract as much as we can and to put it inside the knowledge graph. And then when we get a query like this, right, on the one hand, and so this is converted from the question. So let's say you have a question, you convert into this query. Let's assume that the query is an accurate representation of the natural language question. Well, if you run this query in a very strict form, if you just execute this query against, in this case, Elasticsearch, but you know, you can, the SQL or Sparkle can be converted into a key value query with the exact semantics. It turns out to Elasticsearch, and there are papers on that. But let's say, you know, ignore the Elasticsearch. Suppose this was a triples, you know, this was, we represented this as, let's say, an Amazon Neptune, which is a graph database, and we run this query against the graph database. We learned very early on that you would get no results because the strict query would not match all of these terms exactly. So what we had to do was to automatically reformulate the query into multiple queries, where the strictest query was high precision. So this is the strict interpretation, but then we would loosen some of the terms and make it looser. And we did this automatically. So then you would get a tree of queries. And this tree or set of queries would be executed. And we would get the ranked candidates. And based on how many results are overlapping and, you know, other things like that, we would rank the candidates and then put them on a GUI. So it is very simple diagram, you know, but in fact, it sort of, if you remember what I sort of said about access, right? If you have the symbolic knowledge base, you don't just want you know, strict logic access. You want something where you issue the queries, but then there's, when you get the results back, hopefully you can also do something with that and rank it and reconcile it. Because in these rank candidates, we used, I wouldn't call it a neural technique, but it wasn't a symbolic technique. You know, we wanted to assign confidence scores based on the results that would be returned. So beyond conceptual innovations, there was significant systems engineering that was needed to implement the concept. And so it really took a lot of engineering. I think this is one of the things that large language models can actually make easier. But at the time, there was a lot of code writing and a lot of APIs and just a lot of different things. And that's probably why it took a long time, even aside from the conceptual innovations. So I want to show you what the investigators would see, right? So they would not see the query. They would click on this enter search terms, a form would come up. The form would contain the fields that would be defined by the ontology, the investigative schema, and they could enter whatever they wanted. So they could just enter keywords. They could enter, you know, they want to enter something in the location, if they want to enter something in physical attributes, if they want to enter something in phone numbers, they can enter as little or as much as they want. And then what we give them is the ranked list, right? So here you see that there are ranked lists, and we in the screen we showed 25 results. This is just one of the 25 results that is expanded here. And we collect a lot of provenance. On the side, you see things that would support aggregations, right? So this is what we call faceted search. We would give a relevance score. So like over here, you know, this is kind of the, you know, how we ranked, you know, and so that was based on the relevance score. And we would also give the original URL. So if the investigator was not sure that these are right extractions, and they wanted to go and explore the URL, assuming the URL was still up, because in this domain, URLs can get taken down very quickly. They could go to the URL to check it out. So we weren't like, oh, you can only use our system. You can't. We won't show you. We won't allow you to use anything else. We were like, no, this opens on a browser. You use this system. You can also use other systems. You can use the regular web. You can click on the URL. Whatever makes your life easier to solve this very difficult problem. One of the very neat things about this platform that is not available in something like Google, even in the generic setting, is what we call entity-centric search. So this is similar to the cluster querying, right? This is the interface for the cluster querying, where if you search for an entity like this phone number, the investigator might want to know, well, what are all the other phone numbers that are co-occurring with it? What are the locations, etc.? Because and then they can kind of figure out, whether they need to do an investigation, and this person might be trafficked, and can they, track the person? Can they rescue the person? If they get a tip, for example, right? So this is, it could also be done for social media IDs and so on. So the in-use impact, so we also did a lot of, formal evaluations, which are there in the papers. But since I'm running out of time quickly, I'll just show you a little bit of the in-use impact, which is that the system, along with other systems in the MEMEX program, was transitioned, and it led to actual victims getting rescued, which was something that was an unbelievable feeling, that when you build a system and play a small role in bringing some of these victims to justice and catching their traffickers, it was very rewarding in some sense working on this problem. And so I will just quickly take a few minutes to go through another system, but this one much quicker, and then I'll close out. So hopefully I still have 5 to 10 minutes more. This system was for crisis response, and it was called Thor, or Text-Enabled Humanitarian Operations in Real Time. Now, Thor was designed for a totally different purpose compared to Dig. And the purpose was that, the problem we were interested in was that, as you see here, besides the major languages that we're all aware of in some sense, and for which we have very good computational models, there are all these other languages, some of which are spoken by millions of people, are very old languages, but they are computationally low resource. We don't have good models for them. We have not trained resources for them. And so hence, if a disaster breaks out, for example, if there's an earthquake, such as in Uyghur, how can we, develop crisis response systems that can work in the local language, right? So this was kind of the problem we looked at. And to give you a sense, again, of what, let's say, the Red Cross, if they go into Uyghur, with the hope of helping out after an earthquake, this is the kind of text they would see. So this is in the Uyghur language, and it's not really making a lot of sense, right? And there are many thousands of messages that would be coming in. So if you as the Red Cross come in, you have to now find a translator. The translator would read all of these. That would take a long time. Then you have to compile all the information together, tens of thousands of messages. That would take a long time. And by that time, many people will have died, right? So we clearly need to do something quicker. We need to translate these really quickly. And we need to have situational awareness. Who needs help? Where do they need help? What help do they need? Those kinds of questions. That's a different domain-specific search problem. So Thor, looks like this. So as you can see, we use neural methods to translate the text into English. You don't see the translation here right now. But then what we do is we classify needs, we extract entities, we geolocate them, we put them on a map. If we had more time, I would show you a video, but it turns out you can draw boxes around this. You can click on these things. So if you're interested in who requires medical, who needs shelter, you can click on this bar and it would take you to the medical entries. Now, one very important thing is the extractions are noisy again, right? And you can make that out. There are lots of extractions in these other places, and it's more likely than not that actually some of these are noisy. We have extracted noisy entities, but you can see from the hotspots that on average, we are getting a signal, and it's not all noise. And when you show it in a good GUI, right, you can, the person to whom you're targeting this can actually work with the noise. They don't need a fully clean data set. They can work with the noise, but you have to give it to them in an interface that enables useful search, right? So usefulness is very important. It's not all about accuracy and metrics. We also have to focus on usefulness. What will make something useful to the person to whom this is being targeted? Now, this is the architecture of Thor. And again, without going into all the details, we integrate neural natural language processing like machine translation and so on. So these are the neural things. But we also have the symbolic methods for sense making and interpretation. So we have a symbolic knowledge graph. We have an ontology that defines needs and events, entity types, even economic concepts. We also have modules for supporting social science on this, right? So it's not just for prediction and all of that, but also for understanding the disaster. What happened, what went wrong, what went right. Can we apply scientific methods later on after the disaster is over to build statistical models, right? So it's very different from prediction. And then finally, GUIs, right, which are very important for this. And so this is kind of what the overall architecture looks like. So let's translate. You can have the original text. In this case, I'm showing for Nepal, which is, we had a lot of English text, but there were also Nepalese text, and you can see those if you scroll down as well. Topics, locations, need types, GUI, you can see very strong focus here in the middle. You can actually draw boxes. You can zoom in, kind of like Zillow or some of the other platforms like Google Maps that you might have seen. So a lot of facilities that we actually offered in this platform. So now just let me take 5 more minutes to conclude by considering the importance of both LLMs and KGs in current neurosymbolic research. Now, both of these systems that I showed you, are neurosymbolic systems. We didn't call them that when we published those papers, but they do have a knowledge graph. So that is very central in both systems. They do have their own ontologies. Some in the applications we look at, the ontologies tend to be shallow. They are more like schemas. They are not very deep ontologies. And the reason, of course, is that we want to support a wide range of classes, and we really don't, because of the noise, we can't have, we can't throw out anything. So we don't want too many constraints in the ontology, if any, because chances are there will be lots and lots of violations, and the data is so big that you can't really run a proper reasoner over that kind of knowledge graph. So that being said, the knowledge graph is common to both of the systems and to many other systems that we build. So for us, the robust symbolic representation is the knowledge graph. And as you saw in DIG, there was the knowledge graph construction, that small box that I pointed to. In Thor, we also had the knowledge graph, right, that we use neural techniques to translate, extract information. But in fact, in the knowledge graph construction, in a typical knowledge graph construction, there's a lot that goes on. So not only do we have to define the domain model and have something like OWL or RDFS, but we also have to usually use NLP techniques to do KG construction. This, has evolved a lot. It's gone from CRFs to BERT-like language model to then large language model. But you get this initial knowledge graph. Then you have some graph learning, right, like entity resolution. This is where I did my entire dissertation. And you reconcile duplicates, you remove noisy links, you add new links, all of these things, many, many papers published in KDD and Semantic Web, etc. And then you get the graph database and you have to connect it to the end user task and applications. And this, again, is very much a Semantic Web databases kind of topic. But across the board, in all of these modules, there's a lot of interdisciplinary research. All these communities are involved in all of these steps. So it's interdisciplinary, but for that reason, it's also challenging because sometimes we propose something in one community, but there may be a solution in the other community. We're just not aware of it because they're using a different kind of language. They are, it can be difficult sometimes to reconcile all the different work that is happening across the communities. So the landscape of KG research, again, we like to say that even just in building the KG, you have to apply neurosymbolic techniques, because on the one hand, there are the statistical techniques which come from the NLP, for example, but are also in many other communities. And then on the other hand, right, we also have a lot of the ontological techniques. So even when we are building the knowledge graph, we apply the neurosymbolic. In many cases, it's not always purely neural. I think that's generally a bad idea in real domains. So with LLMs, right, can we have something like this, right? And this is really an open question. I mean, which parts of these steps can LLMs influence, replace, augment, not affect at all, right? And in some cases, I think the answer is a little bit more obvious. Like, for example, here in KG construction and NLP, of course, they have really gone all out on LLMs. These things could potentially be replaced with some prompt engineering or fine-tuning, etc. But this one, KG identification, I am less sure about that the LLMs will actually replace. I think certainly they can augment, but they will not replace. With the domain model, I think it seems unlikely that LLMs will really affect all that strongly, right? And we still need the domain knowledge. We still need the domain model in many applications. So, but that being said, is neurosymbolic reasoning always the answer? And sometimes, I hear people take a very dogmatic position on this, which I think is not fruitful. It sounds dogmatic and religious and not scientific to always claim that this is always the answer. So in fact, I would argue that for some applications, purely neural approaches might be enough. And there's no shame in admitting that. So for something like question answering, there are many question answering systems where you apply the LLM with the right prompt engineering, and it just works really well. It is very difficult to beat, right? On other things like summarization, I mean, this is a use case for GenAI. If I give you a page and I ask you to convert that into a paragraph, I don't think there is any system out there that can do what GenAI can do. So summarization is a GenAI application. Similarly, machine translation is a GenAI application that is done very well. But for something else like truth and fact checking, one would argue that knowledge graphs are still playing a critical role. There are some archive papers on some other topics, but the jury is still out. These are archive papers. So we still have to see whether they will have an impact or not. So that being said, for others, a purely neural approach will be inadequate. And I always like to point to my dissertation topic of entity resolution. Now, why will a purely neural approach be inadequate? It's not for the reason you might really think initially. But before I go into very quickly, and I'll close in a minute, I just want to tell you what this problem is if you're not familiar with it. So it's basically identifying two objects that refer to the same object. So if you look at this network here, social network, you see all these people, and it looks complex, right? But when you do entity resolution, when you combine the duplicates into a single node, you get something like this, which is much simpler. It's a clique, right? So this is a very simple example. But of course, we have entity resolution with DBpedia, with geonames, with lots of knowledge graphs. It's a big problem, not just in semantic web, but in databases, in bioinformatics, even in health informatics. So it's existed for 50 years in many communities. And unfortunately, right, the problem is not just a simple one of classifying when two things refer to the same thing, because if you do that, it's a quadratic problem. So to give you a thought experiment, if I give you two databases, but you can also use the same philosophy in one database that you're trying to deduplicate. But if I give you two data sets, let's say DBpedia and geonames, and I ask you to reconcile or deduplicate by using OWL same as, right, to discover the OWL same as links. If you do a pairwise comparison, it will be O of n square, which even with 1,000, 5,000 entities quickly blows up into the millions. And DBpedia has millions of entities, geonames, similar. So it gets intractable. So it's not, it's polynomial, right? But polynomial is not good enough in practice. We want linear. We don't just want, any polynomial will not do, like quadratic. We want near linear. So the approach is that we usually do this thing called blocking. where we approximate the cluster entities that are likely to be duplicates. So this is much cheaper. For example, you might block up based on the last name of the individual. And then we have much fewer pairs that we apply the machine learning or the similarity function to. Now, Gen AI, right? The problem with Gen AI is that how do you do blocking, right? Because if you get a data set like DBpedia, you can't send all of DBpedia and all of GeoNames into the LLM and say that, here's 1 million entities each and find me the links. The LLM will not accept that as a prompt in the first place. The prompt is limited to a certain number of tokens. So you have to do blocking first, which is non-LLM, that is more symbolic. And then after blocking, if the block is small enough, then you might be able to send a prompt like this. But if the block is big, then again, we run into the problem that what do we send into the LLM? Furthermore, LLMs are not cheap, right? So it's when you do it over tens of thousands of prompts, right, the cost really adds up very quickly, even if it's pennies for one prompt. So there is, another problem, which is that if even with tens of thousands or hundreds of thousands of similarity computations, which would be possible with normal machine learning, with LLM, it becomes too expensive. So there's a cost problem, there's an efficiency problem that can occur here. And so this brings me to synergistic opportunities where, we can't solve everything with LLMs, nor can we ignore LLMs. But what LLMs can do is to help minimize social friction and improve collaboration between different communities, because LLMs are easy to use and they can actually write code. And so we may not have to do all the engineering and the gluing. We can bring the scientific methods, and maybe LLMs can help us convert that into code. So this is something that might be feasible, building these entire infrastructures with some help from LLMs. And so many complex solutions could be framed as LLM prompting. But that being said, we do need the domain model in many applications. We do need to address complexity issues in entity resolution. This kind of thing where you have a graph database and you're accessing that, it's not so clear what LLMs can do here. So with that, I will close out. Of course, this is all, I'm sure many of you are aware of all of this, but there have been so much work. This is already out of date. The generative LLM stuff, KGs, is a hot topic. In LLM applications, KGs can be valuable resources. I think people are studying this also. So no, it's not going away. And I think that KGs and LLMs together can be a very powerful force. And it's exciting times for challenging applications. So with that, I will just stop here perhaps for Q&A.
All right, thanks, Mayank. I tried to do a little bit of a virtual applause here. Not sure if that works. I was alone. Okay, good. But I think the other people enjoyed the talk as well. So we have the first question from Aiden, and he asks about, I don't know if you see it in the YouTube chat. He asks about combining embeddings that come from knowledge graphs with embeddings that come from text. So do you see any benefit there? What are your thoughts on that?
Yeah, so I don't have backup slides here on that, but there has been, so there are two ways to look at that problem. So traditionally, one of the ways that that problem was addressed even before BERT and the language models was that the text embeddings could be used to initialize the knowledge graph embedding. So for example, if you had a description field, which is very common, right, in many knowledge graphs, the description initial embedding, instead of randomizing, randomly having an embedding, we would have a text embedding that comes from, let's say, Word2Vec, or one of the newer models, and then you train the knowledge graph embedding on top of that. So some people have tried to do that, and the results were promising. More recently, the opposite has actually happened. So there is some work where you can use the knowledge graph to fine-tune the language model. So you send the knowledge graph into the language model, and the language model will absorb the information inside the knowledge graph to become a better model. Now, that is not really an embedding approach, in the sense that the language model is, we don't usually get embeddings directly from the language model. We don't use it for that purpose anymore. But the language model has a neural representation of information inside it. It could give embeddings if we ask it properly. And so the knowledge graph can be absorbed into the language model as well. But then you lose the symbolic structure of the knowledge, right? And it gets into the black box. So both approaches have been tried. I personally feel that you can have your cake and eat it too. So you can use the text and knowledge graphs to get a better embedding if that's what works for you. You can use the knowledge graph to fine tune the language model, but I don't recommend throwing away the knowledge graph. Even if you use the knowledge graph and convert to embeddings in any way, whatever way you want, the symbolic structure of the knowledge graph, I think is very important. That should not be thrown away.
All right, excellent. Thank you. Axel Polaris asks that instead of doing the translation from text to Sparkle queries, use alternative approaches for leveraging the knowledge graph like message passing. Do you have some thoughts and ideas on that?
Yeah, so I think the issue with that is actually efficiency, because the queries are real time, right? And so if you do message passing, that might work for learning, but for querying, that is very difficult because let me actually go to the slide first. Yeah, so if you get a question like this, right, find me the last timestamped ad containing this phone number. It's not so clear how we can do a message passing using something like this, right? I mean, if it exists, I am certainly not aware of it. Maybe we can do message passing to refine the knowledge graph, but if we do that, it would have to be offline, because in the real-time system, right, we would want to actually link this phone number against an index. That's the fastest way, right? Whether it's a graph database or some other approach, we would literally want to link this against an index and then get the retrieval and try to then show that on the GUI very quickly. However, you do bring up a very interesting point, that is, there are certain kinds of domains, and this is also one of those, where the query may not be real time. They may actually say, well, I need a dossier on this entity, and I'm willing to wait for 10 hours, right? So that's very interesting. So typically we think of queries, running in real time, and we even measure different database systems, right, in terms of the speed of the query. But there is a class of users that are willing to wait, that will tell you, look, just give me a really good dossier. I'll specify the information, but then go and do your magic, and then tomorrow, come back to me with a dossier that I can look at, that I can explore. I'm not in a hurry. Right? So this is kind of like literature search, right? Like when you're doing scientific literature search, you're not going to get everything in 1 minute. So you kind of go and you do some literature search, then you read more, then you get more papers. So when we think about our PhD students, that's what they do, right? They kind of go away for a while, and then they come back and they know a lot more on the topic. But yeah, I mean, for this, I think I see the private message. Yeah, I think the problem that I often find with some of the querying work, including direct knowledge graph querying using embeddings, is that there is only a certain class of queries that tend to work with them. So, and the other problem is that the semantics. I think with message passing, the semantics of the question do get lost, because it's a machine learning method at the end of the day. Whereas when you convert the question into something like Sparkle, if something goes wrong and we are not able to answer the query, then we can look at the Sparkle, right, to understand what went wrong. Is there some piece of information that is in the Sparkle but is not in the knowledge graph? Did we misinterpret the question into the Sparkle? And so on. So I do believe that the middle step of extracting semantics from the question is something that is often underestimated in the data mining and the machine learning community, where again, they see everything in terms of accuracy. That we can use this method and get 5% more accuracy, but along the way you lose the semantics. And what I have learned is, many domain experts are willing to get away with 5% lower accuracy, but they want the semantics. They don't call it that. but they really want to understand the working of the system. They will even ask us, well, why did the system bring up this result, right? And if you have the sparkle, right? So if you have all the provenance, if we are logging all of these queries, for example, right? So if the expert comes in and asks, well, why did you put this, ad in number 4 spot? Then we can actually go back and look at the log of our queries to figure out that what was the reason that ad went into number 4 and so on. So we can give an interpretation. And that's kind of why symbolic is so important in the first place. Yeah.
I guess the point is it's more about answering the information need or satisfying the information need of the user, and that can have multiple back and forth queries rather than saying I need the accuracy on that keyword or something like this. I think that's a good point. I have one question from Tobias. Great minds think alike in English, or the German translation would be two idiots, one thought, because I thought on a similar question when you said you want the dossiers, and you can wait 10 hours. Sometimes the data is not fresh when you have an index. So you could also imagine that you go to the live web, let's say, and have these sort of information agents roaming around. I know Craig did something along these lines in the last century even. So is that still something to consider, or do you prefer having that index already there that you can work with?
No, absolutely. And in fact, one of the reasons to have this kind of knowledge graph is that you can refresh it, right? So one of my PhD students, who did a qualifying exam recently, was also proposed a neurosymbolic system for healthcare. And she was asked a question, well, why not just do a Google kind of thing and, take all the new data and, like fine tune the language model. And what she said was, which was very insightful, was that, look, if you have the old data, let's say from yesterday, and you fine tune the model, and then you have new data. So by the way, you do have to take new data into account. You cannot ignore the new data in many domains. Now, in some domains, you might be able to, right? Or it could be more slow, right? It could be slow. It might update every 6 months or something like that. That's a different problem. There are other domains where you do need to update sometimes in real time. So in Thor, we have streaming data because it was real time, right? The disaster messages would be coming in real time. So in fact, this is streaming. This is a completely streaming architecture. In Dig, it wasn't so real time. We could update, let's say, every day or every week, right? Because these ads are getting posted and taken down fairly regularly. But just like the regular web, it's not a streaming problem. It's not an ongoing incident. Usually investigations take many months. So it's okay if you update something every day or every week. So what I've learned, which is so interesting, I think as a research community, we should address this problem that, number one, what is the frequency of data refresh that is required? And I suspect that the different frequency will implicate different designs, right? So if you're streaming in real time and you need to forget the old information, then machine learning and fine tuning is not going to be very good, because machine learning is not good at forgetting. This is a very active research challenge. How do we make the machine learning model forget something, right? So this is challenging because you'll have information degradation, you'll have conflicts of information. If you just keep streaming in and fine tuning or training a model on streaming data, that might be conflicting. So I do believe symbolic methods really play a big role there because we have provenance, right? So if we get something, over here, right? If this changes or we learn something else, then we can just add another qualifier and we would get another date, and we can deal with all of that in the querying system, right? So in my view, if you have data that is going to be changing, fairly frequently, and you do need a symbolic representation, actually. Yeah.
Okay, cool. Thanks a lot, Mayank. I think we are at the end of our talks series session today. I will try once again to get a virtual applause going with the Zoom participants here. So 3, 2, 1. No, okay, not even Tobias is clapping with me. But I
did.
think
That noise filter did it, pull it out, I guess.
Okay. Oh, noise. Yeah, that was noise cancellation. Okay. So I give back to Tobias, and thanks again, Mayank, for the good talk.
Thank you.
So that leaves me with a tiny bit of housekeeping at the end. So thanks, Mayank, for the very nice talk. We have the next talk scheduled, Mark Mewson. Check our website, follow us on this thing formerly called Twitter, site and subscribe, and see you next time.